Our next speaker is Jalene Jordan, who leads the malaria team at the Institute for Disease Modeling, and she'll be talking about modeling to inform targeting and combinations of interventions.
Right, thanks, Gina and Philip, for the honor of making the case for modeling in this very public setting. Generally, if you want to understand what's going on in the field, what you want to do is to go there and collect some data on it. So what then is the role of modeling, given that the best way to understand something is to actually go there and observe it? Well, there's a great role for modeling in having one single framework for understanding not just what's going on in one field site, but across many field sites. So how can we tie together stuff that we've learned across many different geographies into one way of thinking, or several ways of thinking, that help us understand what might go on in a completely different geography or in a completely different type of scenario. So one of the things that we do a lot at the Institute for Disease Modeling is to use this unified framework to then test and compare possible intervention strategies. So it's not practical to test every idea that you have for intervention strategies right in the field, but in the modeling context, it is relatively simple. You can test hundreds, you can test thousands of different interventions and see what's working or what could work, what might not work, why are things not working, and move forward from there. And of course, once you've used perhaps your modeling to develop some kind of plan that is maybe moving your country toward elimination or trying to more efficiently reduce burden, you should then go back and collect more data, close the loop, learn more, improve your models, and always iterate and always improve. So given that we're going to try to use models to predict what might happen, what are some things that we need to make sure we are doing well? One thing is that we really need to do well at understanding just what is going on with the biology of malaria. Understanding how does exposure create immunity, what does immunity mean, what does it look like, and how does that then go on to affect how infectious a person is. So if a model is not able to get the relationship between these features right, then you're in a bind. What exactly does it mean to throw some nets at your model and see what happens to transmission? Well, really, what does it mean? So this is an area that we are continually trying to improve as field researchers gather more data about primary parasitology. There's more and more studies about infectiousness and immunity, and it's just wonderful to try to work with our partners to try to make our models better. Another aspect that we want to make sure we get right is just to understand what is the population that is harboring malaria. So things like population size and where people are living, these are important things to get right. We've heard more and more over recent years about how important it is to understand connectivity and how populations move and how that might impact the success or failure of your strategies. And we've also heard a lot about heterogeneity and risk. So how do your demographics or occupational or where you live features, how did that affect how likely you are to contract malaria and transmit it? The third aspect that is really key to get right is the intervention part. So when interventions are implemented, either in a research setting or in a program setting, what does implementation actually look like? So people often have goals that they would like to achieve, but are those goals actually achieved? We all know there's a gap between ITN ownership and ITN usage. That's something that's really important to get right in the model. Otherwise, when we say distribute nets at 60% coverage, what does that mean to the program if they don't really know whether people are actually using those nets? And this is also important in thinking about health-seeking behavior. So Noor alluded to this in his talk. I'm thinking about just what is the uncaptured burden of malaria, what is the role of counting non-malarial fevers as malaria if that person happened to test positive. And those are things that we need to be able to capture in our model in order to have a really accurate impact going forward. So I just want to highlight a little bit of the work that we've done recently in making sure that our transmission model is as good as it can be. So this is work by Prashant Selvaraj. He's a research scientist with us, and we recalibrate our model every few years incorporating more and more data sources. So this, for example, is actually a very old data source. It's from the Dielmo project, where researchers were able to get a pretty good estimate of clinical incidence by age, as well as EIR. So when we then enforce this type of EIR in the model, we want to make sure that we're getting the right shape of clinical incidence by age, and we're mostly able to do that. We've also been excited to reuse old data from the Garkey project. What I want to impress on you here is that there is a way to take a very detailed look at model calibration and ask the model to be able to capture parasite prevalence by density, by age, and by season. And you can judge for yourself where our model is doing well and where it could do better, and this is an area that we're very interested in improving moving forward. So then I just want to show two modeling applications addressing what can we do with modeling in areas that have lots of data as well as areas that have less data. So in areas that has lots of data, we've heard through the years about lots of work that's happening in Southern Province in Zambia, and we work here for two reasons. One is that the epidemiology of the site is particularly interesting. So on a pretty small spatial scale, you have a very wide range of transmission intensity. So you can model both lower transmission sites and higher transmission sites and hopefully learn something about the differences between those two. And the second reason we work here is that simply there's been such a wealth of data collected in the region. And this is done by the Zambia program, of course, as well as in collaboration with MASEPA. And they've both been incredibly generous with sharing their data, not just with us, but with other modelers. And I hope that they see their choices as having a really positive impact on their program. So let's just take one particular health facility catchment in the Lake Kariba area. This one's called Bondo. I'll just walk through some work that we've done here. This is an area of about 750 households and about 10 to 15,000 people. And because there's such a great resource of data in the region, we know many things, such as where all the households are located. We have some baseline prevalence data. We know where the health clinic is located and where community health workers are located. We know how health seeking depends on distance from your point of care. And what we're able to do is then to build a model that includes all of the interventions that have been done in the Bondo area for the last decade or so. So based on surveys, we know when people are receiving bed nets and also which part of Bondo are receiving bed nets at what time. We have a history of what the major changes in the health system have been, including the implementation of community health workers in 2014, as well as the beginning of reactive case detection. We also have 7 mass drug campaigns. There were 6 test and treat campaigns and 4 presumptive treat campaigns, so MDA campaigns, and that's where a lot of the survey data comes from, where many people have been contacted up to 11 times with a massive list of survey questions that they were kind enough to answer. So we've built this model of Bondo. We've included everything that we know about it. Is it any good? So the least that we can ask of our model is that it's able to capture some, say, like parasite prevalence data. So here's 7 cross-sectional surveys, and in the pink line, we see our model is doing a fairly good job at going through all 7. And because it's a model, we not only are able to capture that RDT positive fraction, we're also able to capture the sub-patent fraction. So you can kind of get a glimpse of what's perhaps the role of this sub-patent population in sustaining transmission in Bondo. So in addition to these 7 cross-sectional survey points, I also have 4 more that I did not use to calibrate the model, and I can see the model is in good agreement with those in saying that there's very little transmission left in Bondo. And Noor also mentioned the use of routine data. So we didn't use our routine data to try to calibrate this model, but instead I'm going to use it as an out-of-sample comparison to challenge the model to capture the routine data, even though we didn't use it to inform the model. So that is what this looked like. In the gray bars, we have the routine data. In the yellow line, we have our model. And it's doing a fairly good job at saying we expect to see cases at this time of year, approximating the number of cases we're seeing. We've clearly missed something that's going on in 2014. I don't really know what is going on there. That's something to ask the people in the field who have much more knowledge of this particular geography. And we also know that, of course, not all cases are treated, but we can start to ask questions like, what would happen if we treated more of those untreated cases? So that's exactly what we're going to do. We're going to take this model of Bondo, including all the information we've ever gathered on it, and we're going to test a number of different intervention scenarios and then monitor for elimination. So some of these intervention scenarios are going to be counterfactual interventions and saying, well, what if we never rolled out community health workers? What would have happened? What if we did community health workers, but we didn't do the reactive follow-up? What would have happened? So what I'm going to be showing you in the next plot is the fraction of simulations of any given intervention set that result in elimination. So this would be, in your mind, the likelihood of seeing elimination in Bondo in the year 2020, which I've defined as no locally acquired infections, symptomatic or asymptomatic. So here is the current strategy to our best guess of what's going on in Bondo, all the interventions there and in the connected areas. We expect to see, probably Bondo will not be having any malaria in the year of 2020. And now we can run some of those counterfactual scenarios. So what if we ask those community health workers to stop doing their reactive follow-up? Well, we don't see that much of a penalty. So this suggests that perhaps in Bondo, those reactive follow-ups are not contributing a huge amount toward Bondo's ability to reach elimination. If we say we'll stop that community health worker program entirely, instead we're just going to rely on that one clinic, suddenly we're starting to take deeper penalties. So we want to say, well, case management is still incredibly important in this area, even though it looks very likely that you're going to be able to get there, make sure that you don't stop it. And in fact, if you just ask your community health workers to perhaps start doing reactive follow-up, but instead concentrate on improving that case management rate, you would increase your probability of elimination even further. And I want to note that Bondo, of course, is not an isolated area, right? It's surrounded by all those other villages in the Lake Kariba region, and it's very well connected. People are well able to move around the region, and including people from Bondo going down to those areas by the lake with the higher transmission for fishing or farming. What could the role of that kind of movement be in sustaining transmission in Bondo? So I asked the same question. I said, well, what if down by the lake you just relaxed your malaria control? And suddenly our chances of elimination in Bondo are much less. So this is the take-home message here. Case management is really important. Think about connectivity. I didn't really know how many importations are going on in Bondo, so I tested a range of different possibilities, and the trend is very clear. There is some rate at which you're really just going to tank your chances in this connected, perhaps easier area. So then to say, what could modeling bring to elimination planning in the Lake Kariba area? So we saw in Bondo, case management is incredibly important. I didn't show this, but there is a role for MDA in accelerating elimination in Bondo, and that refers to the MDA that's already been done rather than doing more MDAs, just to be clear. Not only did I do some modeling in Bondo, I also looked at some of the neighboring regions that are a bit higher transmission. So in this neighboring region, which is a bit higher transmission, but also much more sparsely populated, I see a different package of interventions as the minimal one that gets me likely elimination. I see, again, a very core role for case management. There's a very clear need as well to maintain vector control. And then you kind of have two options for addressing the asymptomatic reservoir. Either you do RCD really well, or if you can't do that, you can come in with some MDAs, and that's helpful. In addition to that, I looked at a third catchment, which is, again, more challenging. You can see that it's requiring more interventions. So what could Zambia do from here? Say, well, I've modeled 3 different catchments. Is that only telling me things about these 3 individual areas? So a little bit of yes and a little bit of no, because you could imagine Zambia saying, well, what about that next catchment over right here? Is it perhaps kind of similar to one of the 3 I've already modeled? Is it most similar to the low transmission one or to one of the high transmission ones? And that's helping to start thinking about what's the intensity of interventions that I need to do in that neighboring area. All right, so that's what we would do if we have really great, wonderful data going back a decade, but we often don't have that. So what can we do with models in that more limited situation? Well, the Malaria Atlas Project and the Big Data Institute at Oxford are really getting very good at guessing what's going on in places that there's less data. So we often have data from a few sites, such like Sentinel sites, and then we have now a suite of geospatial models, and the models and data are both getting better day by day. So what we can say is, well, perhaps we have some idea of what rainfall looks like by month. or how good the temperature is for sustaining anophelines, again, by month. And perhaps we also have some guesses as to what's the relative abundance of, say, primary vectors in Africa. And we can use these guesses to then say, are there types of places in Africa? So this is worked by Amelia Bertazzi-Villa. She's a student with the Malaria Atlas Project and also working with us. What she's done is to use those environmental covariates and the vector abundance maps to kind of classify the continent of Africa at a 5-kilometer pixel level into kind of zones. And when we look at this map, a lot of it makes a lot of sense, right? You see that orange Sahelian zone, very seasonal, lots of Arabiensis. So you see that Central Africa zone dominated by Gambia, and then you also see Eastern African, Southern African zones. And there's a lot of refinement that can go on into this thinking, but I'm just going to show you a very simple example of what you could do when you have a map like this. So again, to show you two pretty different areas, that Sahelian zone, again, very seasonal rainfall, and then that Central African zone, the pink one, you'll see, let's say, a double peak of rainfall. And places within the zone are not going to be identical to each other, but they're going to be much more similar to each other than they would be to a place in a different zone. So let's say, we'll take the Central Africa spot, and we'll say, well, what would happen if we just added ITNs? Let's say it's a naive place that's never seen ITNs. Of course, this probably doesn't exist, but what could ITNs be doing in terms of reducing burden by averting cases and by reducing prevalence? And we might see some pattern like this. So as your initial transmission changes, you'll see first an increase in your burden reduction and then a decrease as the ITNs have limited ultimate impact when transmission is really, really very high. But you'll expect to see somewhat of a different pattern when you move to a different zone. So in the Central African zone, we have it as primarily Gambia, so a lot of indoor biting and very vulnerable to effective ITNs. In the Sahel, more Arabiensis, so more outdoor biting, and we see a decreased impact of those nets. So say now you're in a region and you say, well, I already have nets, should I also do some spraying? And that's, again, a question that you can easily ask in this kind of modeling framework. So now let's add in some IRS on top of the ITNs and see how the impact is different in the different zones. And now, from a program perspective, you could say, well, how would I possibly use these very colorful plots? You could say, well, you know what, I'm in Burkina, I'm in the Sahelian zone, I'm going to think about the orange lines. And I'm in a place with initial PFPR of perhaps 40%. So I'll go over to that 40% tick mark and then go up to the orange lines and say, well, that's actually a huge gap in the potential impact of IRS on reducing burden. So that's maybe something that I would want to consider in my program strategy and perhaps continue to use this framework with other interventions to map out what would be the impact of, say, health system strengthening or other types of vector control. So then to wrap up, what would a practical roadmap for helping programs use models to inform their decision-making look like? So ideally, we'd want to say, for any location, here's the intervention package that gets me to where I want to be with whatever my goal is. And what the modeling allows us to do is to split this into a two-step process by using stratification and saying, well, for this kind of stratum, whether that's someplace like Bondo in Lake Kariba, or it's the Sahelian 40% parasite prevalence place, I know from my scenario predictions what intervention package I want to use, what would be best for my situation. And then there's the other half of this mapping, which is, how do I know which stratum I'm in? And I think this is a really key question that many of us are going to be thinking about moving forward. And then finally, I just primarily like to thank the people in Zambia who have been very patient and very willing to participate in this study and has really allowed us to learn so much about malaria transmission and operations in that Lake Kariba area, and particularly Busiku Haminza and Elizabeth Chizema from the Zambia program because of their attitudes towards data, which I think have really enabled many, many groups to understand so much more about potential elimination. And with that, thank you very much.